Hello, welcome to this MATLAB video tutorial. Today's lecture is concerned with functional approximation. So let me first introduce this concept. The goal here is that we want to approximate a function. The reasons may be different. I mean, maybe you don't know the function, you just have some data points of this function. Or maybe this is a very complex function, very difficult to evaluate, or very difficult to compute its integral. So for whatever reason, the goal here is to approximate a function by another function that is much simpler, much easier to manipulate, like, for example, a polynomial. It's very easy to evaluate, very easy to compute the integral, its derivatives. So there are different types of approximation depending on the type of approximant that we choose. It can be a polynomial, but it can be also a trigonometric function if we expect f to have some periodicity. That must be a good choice. It can be also an exponential function if we think that this function has some exponential increase. So depending on the type of approximating function we use, we have a different type of approximation, but it also depends on the criteria that we use. And basically there are two criteria. The first one is called pure interpolation. This is the one we will explain today. And the other criteria is least squares. In pure interpolation, we want the interpolating polynomial to verify exactly all the data we have. So we expect the polynomial to go through all the data points. This can be done just using one single polynomial that goes through all the data points, or it can be done using piecewise polynomials. So each 2-3 data points, we construct a polynomial. So today we will cover these two cases, and in the next video we will talk about least squares. Now in pure interpolation, we have some data points. These red points here represent the data points. And we want to construct this blue curve, which is the polynomial that goes through all these data points. So we want to find px such that the value of the polynomial at the data points is exactly the value of the function at that point. So it's very easy to understand that if we have just 2 points, a straight line can pass through 2 points. Yeah? Or if we have 3 points, then a quadratic parabola will go through that 3 points. So in general, if we have n plus 1 points, then we can try to find a polynomial of degree n. Yeah, 1 less than the number of points. So we want to find a polynomial of degree n, and in general we will write down it like this. Yeah, the constant coefficient that multiplies x, and so on. So basically the goal here is to find the coefficients that define this polynomial in such a way that it goes through all the data points. If we impose these conditions in all the points, we basically have a linear system of equation that looks like this. Here, this is called the Vandermonde Matrix. These x0, x1, xn are the data points, data points. Then here is the square, the cubic of these data points, and the last column is these data points at the power n. The right-hand side is the image of the function in these data points. So this is data, and these are the unknowns we are looking for, which are the coefficients of the polynomial. So when we solve the linear system, we obtain the values of the coefficients. Okay? So that's what we want to do using MATLAB. So let me explain you how we can code that in MATLAB in a very simple way. The data is called here xpb for the sample points, and ypb is the image of that sample point. Then I will use some auxiliary variables basically to plot the results. So I start defining a function. Maybe in a real problem, we don't have a function, we just have some data points. But here, as it's an academic example, it's convenient to use a function because then I can plot the error. So we can look to how good is the approximation, okay? So I start defining a function. Then I define the sample points. In this case, I will define 0, 1, 2, up to 5. YPB will be a vector that will contain the images of these points by function f. And then NPB is a scalar that is defining the number of data points. Now there is in MATLAB a command called Vander. This will compute the Vandermonde matrix, but let me show you something that is important in our case. When I compute this Vandermonde matrix, the last column is the column plenty of ones. Then I have the data points. Then I have the data points squared. Then the data points cubed. So somehow the order is changed. If I look here to my Vandermonde matrix, I want the first column to be plenty of ones. So that's why, in order to follow your lecture notes, we exchange the order of the columns. So in this line, the rows remain the same, but the columns are exchanged. So the last column is going to be the first one, and then the first column is going to be the last one. So if I do this, you can see that now the first column is the one plenty of ones, then the data points, and so on. Okay? The reason that MATLAB uses the Vandermonde matrix in the other way is because instead of writing down the polynomial like this, they use the first term of the vector corresponds to the coefficient of the maximum power. So they are in reverse order. Okay, so I wanted to follow our lecture notes notation, so that's why we change the order here. Now we compute the condition number of the matrix. This is important because when this condition number is high, then Vandermonde matrix is ill-conditioned and maybe results don't make sense because propagation errors are very important. Now, we solve the linear system of equations here. Here, I'm telling MATLAB to solve the linear system of equations with matrix M, and right-hand side, YPB, I'm using transpose in order to have a column vector. Okay, so basically here I'm solving the linear system of equations, and these are the coefficients of my polynomial. Now it's very important, this coefficient, which is at the first position of vector A, is the constant coefficient of the polynomial. The second position in vector A corresponds to the coefficient that multiplies x. The third position here corresponds to the coefficient of power 2. So you can see that as in MATLAB, vectors positions start at 1, not at 0. We have this different power and index for the coefficient. So here we define the interpolating polynomial as a MATLAB function. And in this for loop, I'm just adding each time the next coefficient. Yeah. For example, I start here, initialize it at value 0. When I equals 1, I add a1, so the first position of the vector, times x to the power 0, which is 1. Then when I equals 2, this is a2, okay, times x to the power 2 minus 1, 1, so times x, and so on. In this way, after doing this, P is now defined as a function handle, and I can evaluate it whenever I want, whatever I want. Yeah. So now let's plot this, and in order to do so, we define the range of the plots. Okay. We will plot between 0 and 5 because my data points go from 0 to 5. And then I will plot here the data points. We can see here in black color and circles the data points we are using. And then I will hold on. It's telling MATLAB, please, I want to plot more things in this figure. So hold on. And then I will plot the analytic function f. Oh, I missed to do this. Sorry. So let's do this. Okay, this is the analytic function. And then I will plot the approximating polynomial. And I will plot the title, labels, and legends. So in blue, we, sorry. Let me, something is not correct. Let me repeat this. Okay, now it makes sense, the legend. So the circles are the sample points. In red color, it's the function, the exact function. And in blue is the polynomial. So we can see that at the data points, the polynomial goes through, exactly through the data points. That was the purpose of pure interpolation, okay? And then we can also plot the error. We can plot the difference between the exact function and the approximated function. So we will plot this error between 0 and 5. And we can see here that at the data points 0, 1, 2, 3, 4, and 5, the error is 0. Of course, because that was the objective, that at the data points, the polynomial goes exactly through the points, so the error there is 0. At the other points, of course, we can have some error, yeah, and that's what we get. Okay, so that's what we did to compute the pure interpolating polynomial, but there is built-in function that can do that for you in MATLAB, and it's called polyfit. So let me do that for you. Okay, so instead of using this Vandermonde matrix, let's comment this. We will use this command called polyfit, okay? We don't need to compute the Vandermonde matrix. It will do that for us. It will compute the pure interpolating polynomial through this command, polyfit. And basically, we need to give the data points and the value of the interpolating polynomial, which is always the number of points minus 1, okay? So this will have the coefficients of our polynomial, but in the order that MATLAB normally uses, which is in the reverse order that we normally use in our lecture notes. So that's why we reverse the order, okay? If we do this, we will get, oh, sorry, this should go also here, okay? This was from the Vandermonde. So when we solve using the polyfit, we just need to call polyfit command, data points, degree of the polynomial, reverse the order of the coefficients, and then we can again define the interpolating polynomial in this way. So we can check that if we run this code, we will get exactly the same results. And we don't need to predefine the Vandermonde matrix. It will compute for us the pure interpolating polynomial. Okay? So let's do now an exercise. Let's compute the pure interpolating polynomial of this function, 1 over x squared, and see what we get. Okay? So I will start defining f as a function handle in MATLAB. Here it's very important to write the dot because we want to do the component-wise operation. Otherwise, when I plug in here x as a vector, I will get an error. So this is the function I want to compute the pure interpolating polynomial in the interval -5, 5. So I want to work in the interval -5, 5. So from -5 to 5. And I will start using 5 data points, equally spaced. Okay, this number tells MATLAB how many data points we want. Then I will compute the image of these points through the function. And then I need to call the polyfit function. Yeah. Remember that NPB is the length of this vector. Now I can call the polyfit function. And I think I will copy all this so we can see the results. Okay, so basically I called polyfit with these data points, the degree of the polynomial 1 less than the number of points. I reverse the order of the coefficients. I define the polynomial and I plot it. Now I want to define the range of the plots between -5 and 5 because that's the range of my data points. Yeah? So yeah, that's it. So let's run it, see what we get. So this is the error and this is the interpolation. It looks fine, yeah, it goes through the data points. We have quite a big error, but we can think that's normal because we have few data points, yeah. So we expect that maybe if we increase the number of data points, this will get better. So let's try that. In fact, in the exercise, it tells us, please try with 15 and maybe 20 equally spaced samples and see what happens. So let's try that. Let's try with 15 data points and see what happens, right? And what we can see is that the interpolation is improving in the medium part of the interval, but in both ends of the interval, the error is increasing a lot. I mean, you have a huge error here and here. You can see that now the error is almost 7 here, yeah. And if I increase the number of data points, this just keeps getting worse. We can see the error is even increasing. So what we can learn from this example is that it doesn't make sense in many cases to use high order polynomials. Like in this case, we are using polynomial of degree 19. Yeah? So when we want to work with lots of data points, normally we don't use pure interpolation with just one single polynomial. What we do is to use piecewise interpolation, which are also called splines. So let me show you how we use splines, okay? Even we had some errors here, yeah, because of batch conditioning, because we are really using too high degree. So let me show you now how we can use splines. Here what we are doing is to interpolate using MATLAB and piecewise interpolation. So each one data point or 2 data points or maybe 3 data points, we will construct a polynomial of degree 0, 1, or 2, or maybe cubic. That's the maximum degree of polynomial we want to use. So the piecewise interpolation methods we will see is the nearest neighbor interpolation. This will interpolate the value at a point using the nearest sample point. We will also see linear interpolation, so this is the linear spline. We will also see a cubic interpolation, two types of cubic interpolation. This one is C1 continuous, this is C2, okay? So let's see how we can do that. First, I define a function, then the data points, the value of the function at those data points, the number of data points, and then I define the points where I want to compute the final result. So here, instead of using the function fplot that we are using here, which is very convenient because we don't need to evaluate the function at a given point. We just give the function minimum and maximum range I want to plot, and that's it. Here, the command interp1 that computes the spline, in fact, doesn't give you the formula, the coefficients of each of the piecewise polynomials. Instead, you give here the points where you want to compute the value of the piecewise polynomial. So x in here are the query points, those points where you want to compute the value of the interpolating piecewise polynomial. In fact, here these points are going to be used, for example, for plotting. I will plot the solution at that point, okay? That's why I'm defining these points as a very finer mesh. They are very, very close one to each other with respect to the data points. We have few data points and a lot of query points, a lot of points where I will use to plot the solution. So this is the command interp1 that is built in MATLAB. You just give the data points x and y, the points where you want to evaluate the polynomial, and the method that you want to use, okay? Now we will compute also the pure interpolating polynomial just for comparison reasons, and I will evaluate the polynomial at the query points, okay? This pure interpolating polynomial. Here, to evaluate the polynomial, I'm using the command polyval, so that's why I don't need to reverse the order of the coefficients, because I'm already using a MATLAB built-in command, polyval, that evaluates the polynomial at the points x int, okay? So we define the function, the data points, the points where we want to plot the solution, and we compute the piecewise interpolation. Here, what we get is these are vectors that contain the value of the piecewise interpolating polynomial at the data points. So let's compute this and plot also the exact values and see what we get. Here we can see the plots of the data in these crosses here. The analytic function is the red curve. Then the nearest method is degree 0 polynomials. So we get these lines, okay? This is the degree 0 approximation. Then the linear spline is the green line. So we can see that these green lines just connect each two data points with a line. Yeah, that's the linear spline. And then we have also cubic splines. We are not explaining them in theory. It's not part of the course, but it's in MATLAB you need to know how to plot them. So here you can see how to plot the cubic approximations. C1 and C2 continuity are the yellow and blue curves here, okay? And the black curve is the pure interpolation polynomial. So the main difference in this file with respect to the other file is that we are not finding the formula for the polynomial. Yeah, here we found the coefficients and we know the formula of the polynomial. Here we are just finding what's the value of the piecewise polynomial at some given points. Okay, so let's do the last exercise here. Let me comment this so we can run the code easier. I want to comment this. Okay. So second exercise here is interpolate this function in the interval -5, 5 using 5 equally spaced sample points, and then use pure interpolation but also piecewise linear and piecewise cubic and see what you can observe. Okay, so in order to do this, let me copy this, and then we will go through it and use just what we need. First, we want to define a different function, not this one. We want to define 1 over x squared plus 1. It's very important to use the dot before this and this because we want the component-wise operations. Then we want to use the interval -5, 5, and use 5 equally spaced sample points, so 5 points. So I will define the query points that I use then for plotting. They should go between -5 and 5. And then I want to compute only the linear, so I don't want the nearest option. I want the pure interpolation, linear and cubic. So I will just leave this one and this one. And also the pure interpolating polynomial. So here in the plots, I don't want the nearest option. I don't want the spline. I just want the linear and the cubic. And the pure interpolating polynomial. So this is gone. And this is gone. Okay. And the same here. I don't want the... Well, let me just do it to here. Okay. To see what we get. Okay. So let's see if we run this code, what we get. We see the different approximations. For the pure interpolating polynomial, we get this curve. For the linear approximation, we connect each 2 data points with a line. Okay. Now, if I increase the number of data points, the piecewise linear approximations will become better and better, and the pure interpolation will have that huge error at the ends of the interval. Let me show you that. If I use, instead of 5, I use 15 data points, I start having trouble with polyfit. We can see this huge error in the ends. So pure interpolation is not working properly. So let me show you just what happens without the pure interpolating polynomial. So this one, I will comment also this one and this one. Okay? Oh, no, this one, sorry. Oh, sorry. Yeah, that was correct. I don't want to compute the pure interpolating polynomial, so I comment this. So exact values, I want to compute the exact values. What I don't want is this one, the pure interpolating polynomial. Okay, so this is gone. Now let's run this. And we can see that the piecewise interpolations just become better and better and better. Yeah. Still, the linear approximation is not very good here. Yeah, we need more data points, but now we can increase as much as we want the number of data points. I mean, we can use 100 data points, no problem about that. Yeah, because each 2-3 data points we construct a polynomial. So that's why we get very good approximations. We can, I don't know, maybe a zoom here. And we can see that we go through the data points very, very well. Yeah. So the good things about piecewise interpolation is that you can have as much data points as you want, but you will get a good approximation without the oscillations that appear when using a single polynomial for all the data points. Okay, so that's what I wanted to cover today. See you in the next lecture. Bye bye.